we are going to talk about homogeneous equation. Homogeneous equation. That is, homogeneous means identical. Yeah. So you are going to know how identical two inputs are. So the first input here is the output one, and we have the input. So we are given a question that we are going to use a great mathematician called Euler. Yeah, Euler, to determine the degree of homogeneity and to determine whether the function given is homogeneous. So let's see the question. It says find whether the Cobb-Douglas production function is homogeneous. If yes, determine the degree of homogeneity. Given that k will equal to ak alpha L exponent 1 minus alpha, where a and alpha are constant. This one explaining it. So the reason why it is a Cobb-Douglas production function is when we sum their exponentials, we are going to get 1. That is, alpha plus 1 minus alpha is going to be 1. That is why it is a Cobb-Douglas function. So let's see. We have this, given that k will equal to this. In this case, it's a production function. K here is the capital and L is labor. So the great mathematician said that for this function to be homogeneous, k times differential of this function, di k plus L di k di L must be equal to n times k. N is equal to degree of homogeneity. Degree of homogeneity. Is equal to degree of homogeneity. So when it holds like this, then the function is homogeneous. So we are going to solve this question. We are going to tackle it one after the other. Yeah, we are going to tackle it one after the other. Let us partially differentiate the function given. So from the question, k is equal to ak alpha L 1 minus alpha. So di k equal to alpha times a is going to be a alpha k exponent alpha minus 1. From the law of differentiation, the degree will multiply, or the exponent will multiply the coefficient. Then we subtract 1 from the exponent, since we are differentiating it with respect to k. Then we bring our L 1 minus alpha. Let us name this equation 1. We are going to solve this one, di k di L. So meaning we are going to differentiate it with respect to L, with respect to L. So let's see, di k di L equal to ak alpha times 1 minus alpha L 1 minus alpha minus 1. So that is it. We have this one, it holds here. Then this one will come down, meaning that it's going to multiply the a. Then we subtract 1 from the exponent. And this is the same as, like k di L is the same as a times 1 minus alpha k exponent alpha L 1 minus alpha minus 1. Equation 2. Let us name the general equation as equation A. So we are going to substitute equation 1 and 2 into the general equation A. So meaning we are going to get k times di k is equal to the equation 1, of which we are going to get a alpha k exponent alpha minus 1 L 1 minus alpha plus L plus L. And we also know that Q di L is this, the equation 2. So that one also times A into bracket 1 minus alpha K alpha L 1 minus alpha minus 1 equal to NQ. We are going to expand the bracket given. From the law of indices, when we are multiplying and they have the same basis, we add their exponents. So this one is exponent 1. This one also is exponent 1, just that we don't write. We are going to expand this bracket. So K times this, we are going to get A alpha K exponent alpha minus 1 plus 1. This plus comes from this, so this K will multiply this. And since they are the same, we take only the base, then we add their exponent. So this, the whole of this exponent plus this one. That's why we have this function, okay? Then plus this same thing is going to apply here. Here is 1. So meaning, and the base is L. We are going to only select one base, then we add the exponent. So 1 plus this whole exponent. So we are going to get A times 1 minus alpha K exponent alpha L exponent 1 minus alpha minus 1 plus 1. And this plus 1 comes from the one here. Okay, equal to NQ. Let us cancel. Negative will cancel positive. Negative will cancel positive. So we have A alpha K exponent alpha plus A times 1 minus alpha K alpha L exponent 1 minus alpha equal to NQ. So we have A alpha K alpha exponent K exponent alpha plus A into bracket 1 minus alpha K alpha L exponent 1 minus alpha equal to NK. So we could see that we have like terms. We have like terms in this. That is A K alpha L 1 minus alpha K alpha L 1 minus alpha. So we have this, the same thing also appearing here. So we are going to factorize the common ones out, and the common ones are A K alpha L exponent 1 minus alpha. So meaning that we are going to get here, we're going to get A K exponent alpha L exponent 1 minus alpha. All is going to multiply by, we are left with this alpha here. We are left with the small alpha here and the whole of this 1 minus alpha. So all multiply by alpha plus 1 minus alpha, which is going to be equal to NQ. We know Q from the question. Q is equal to A K exponent alpha L exponent 1 minus alpha. So we are going to substitute this into this, of which we are going to get, and from here to alpha negative can cancel alpha positive. We are left with 1. So 1 times AK alpha L 1 minus alpha equal to N, and we know K is equal to AK alpha L 1 minus alpha. Now we are going to compare the left hand side to the right hand side, comparing. So this one, you could see this function is the same as this function. Yeah, this function is the same as this function. So by comparing, we have 1 here, meaning that N is equal to 1. So by comparing left hand side to the right hand side, so comparing both sides, comma, n is equal to 1. So the question was determine whether it is homogeneous. So we know this one is the same as this. So meaning this the function given was homogeneous. And now the degree of homogeneity is 1. So therefore the degree of homogeneous is 1. Hence a constant returns to scale. Hence a constant returns to scale. That is to say that when we have 10% changes in the input variable, we are going to get the same 10% changes in what? Output. Because it is 1. 1 here means that the changes that will occur in the output variable will be the same changes that will occur in the input variable. So this is all about Euler's theorem of homogeneous function. Yeah, Euler's theorem of homogeneous function. Thank you very much. In our next tutorial, we are going to talk about optimization, and there will be another example on Euler's theorem, another example on it, so that it will enrich your understanding. If anything, to the comment section is there. Please pass on your comments. If you need more explanation, I will bring tutorials on it again. And don't forget to subscribe to my channel, as I have a lot of things for you. Thank you very much. You know that the name of the channel is Prof Genius. Yeah, Prof Genius. Yeah. Thank you very much. See you again. Bye-bye.